All right, sorry for the late chat. I forgot it takes about 30 minutes for this laptop to start up. So I've received a question, 4 questions before for the start of the live stream. So let me go ahead and get those started. So first question got asked is, bring up the questions. For the lab assignment, not the report due September 8th, do you just want us to upload the separation work list with our numbers filled in, or do you want something else uploaded? So with all these labs, you really just need to fill in the worksheets that are on the course website. Now, subsequent question is, does it matter how many sig figs we use? Yes. So particularly when you work with a scale, you need to make sure that you're reporting the correct number of decimal points that the scale reports. When you do calculations, you still need to carry the correct number of significant figures. Now, my rule is you lose a point for every sig figure off. Now, luckily this is organic chemistry. They don't do a lot of math, so you're probably looking at most like 10 points off for sig figs. But those are really kind of easy points to get. So there's no point in you truncating a scale. I've never heard a good explanation from anyone as to why they are truncating numbers off a scale. Any measurement you take, report it to the correct position if you're taking the measurement, and report any calculated values to the correct number of significant figures. Third question, can you go through number 42 on the homework? So let me bring up the homework. So let me swap it to the desktop so this way y'all can kind of see what's going on with that problem. So question 42, draw the three-dimensional representation of the S enantiomer of what is shown below. So I'm going to go ahead and draw this on the board behind me just so it's a lot easier to see. So the S enantiomer, well, first thing we need to do is build the molecule, and then second, well, actually first of all, let's figure out where this chiral center is. So our chiral centers, again, are going to hover around on carbon. So CH3 automatically out of the running, it's got 2 of the same elements bound to it. Fluorine out of the running, it's got 2 fluorine, or sorry, this carbon's out of the running because it's got 2 fluorines bound to it. This carbon is out of the running because it's got 2 hydrogens bound to it, which leaves us with this carbon here. So this carbon's meets our condition. It has 4 different things bound to that particular carbon. And on top of that, those 4 groups are different. So let's go ahead and build this molecule. And I'm probably going to build it with my flexible piping. Now there's 2 ways you can approach this. One would be to try to intuit it, the other is guess and test. Honestly, both will work just fine in this case. So let's start with the guess and test, and then we'll move on to how you would do this kind of more directly. First, I need to build the molecule. So let's go ahead and let's build the atoms that aren't chiral. So I've got my molecule, and I've just for to crudely build it. So I've got my 3 carbons. I've got my 2 fluorines here represented in blue hanging off to the right, and then I've arbitrarily picked where I'm going to put the methyl group. So in this case, I'm going to put my methyl group down. The question is, what's the chirality of the one I built? So I've just kind of naively built it like it is. So I just assume that the plane of this what we call a planar or a cyclopropane looks like. So now let's start ranking the priorities. So hydrogen is our lowest priority at 4. Each of these are bound to a carbon, so this carbon is bound to another carbon, 2 hydrogens. This carbon is bound to 3 hydrogens, and this carbon is bound to 2 fluorines and another carbon. So this is going to be our number 1 priority. We're going to look at the first difference. So this ends up being 1. This carbon outranks this carbon because the first difference is a carbon, not a hydrogen, so it's 2 and 3. So if I were to look at this molecule, this is going to be the third highest, hydrogen is going to be the lowest priority, second highest, first highest. So I just kind of built a molecule, and now I'm going to do guess and test to see if it works. Now, if it's wrong, all I got to do is switch the positions of the methyl group and the hydrogen group. So take it, and I'm going to bend it so this way that that hydrogen is behind it. I've got number 1 priority, number 2 priority, number 3 priority. So that's counterclockwise, that's the S conformation, and what it's asking you to build is the S conformation. So I just happened to get this one right. So how would I draw this? Well, this is a tetrahedral carbon, so 2 of the bonds have to be solid, 1 has to be a wedge, 1 has to be a dash. So if I build this molecule, we prefer to keep the carbons in the backbone, so we'd have solid lines, 1, 2, 3. And then, because this is a plane, if we look at it, 1 goes up, 1 goes down. 1 fluorine is going to be in plane with the methyl group. Now if we look at it, we've got plane coming out at us, and the hydrogen going back, and the fluorine going back. No, I drew this wrong. Oh, I see the issue it's giving you. Okay. So, problem here is that we have a frustrated ring. So what happens with the ring, if we actually kind of look at it, we don't have anything in plane. That's the issue it's giving you. So, when we draw this ring, if we draw the back line solid for the cyclopropane, we've got the CH2 group coming at us. Okay, I see the problem it's giving you. Now, traditionally, when we do something like a linear alkane, we get that staggered backbone and the backbone solid. But if we look at this molecule, if we look across the back bond, and we straighten out that back bond, actually our hydrogens are pushed back as our methyl group, and so are the 2 fluorines. So the CH2 group here is going to, this CH2 group, the number 2 carbon is going to come forward, but your hydrogen and your CH3 are going to go backwards. And I'm guessing that was the issue it was giving this to. So let me build it and see if that works. Come on, where's the one that lets me pick a different element? Well, it would also help if it kept the fluorine I drew in there. So yeah, that's more the issue, is that you're kind of dealing with cyclopropane and the 2 fluorines are pushed back. So if that's the example it's giving you, that would be something to consider. That actually only this back bond here is going to be solid. Everything else is going to have wedges and dashes. Now, last question. For the NMR discussion board, should there be 3 at the table for the summary of the 1H be a singlet and number 4 be a triplet at 1-to-1 ratio? So let's bring up the discussion board. There was a lot of confusion with the discussion board because there was a mistake in it. And I've had to twice correct the mistake now, but it should be correct now. So let's go over that discussion board one more time. So those of you in Organic 1, you have a discussion board where it asks about, and I'll show you the picture knowing that it's going to be really hard to see. You're given a C13 NMR spectrum, a 1H NMR spectrum, a summary of that information, and this dimethyl compound on the very bottom with the carbons labeled A, B, C, D, and E. So I'm going to draw that really quick on the board again. This time I actually have a whiteboard to work with. So how do we do the carbon 13 and the NMR assignments? So let's take a look at, make sure I got the question right before I go forward. So the question is asked for the summary table of 1H, a singlet, and number 4 be a triplet. So if we go to the table, well, let's just see if this is correct. So we've got a chemical shift at 1.254 ppm. And as far as it is to see, there is a shift there with an area of 2, and that's a doublet of triplets. No, it's not. I corrected that. Okay, corrected again. It's a multiplet. If we look at peak 2 is a triplet with area of 3. It's got the area 3 and it's a triplet. Peak 3 is the singlet with an area of 9, so that's consistent. And then peak 4 is a triplet with area of 2. So the table here is correct. Now, I do need to correct this doublet of triplets. It's actually a quartet of triplets, but the point here is that it's a really complicated signal. Now, this 1-to-2-to-1 ratio, the student is correct that if we have triplets and we have doublets, there is a ratio that occurs. So for a single NMR peak, we expect the peaks to be in a 1-to-1 ratio. For a doublet, a 1-to-1. For a triplet, a 1-to-2-to-1. For a quartet, a 1-to-3-to-3-to-1. And this is going to follow Pascal's triangle down. So 1, 4, 6, 4, 1, if for whatever reason you were able to reduce that many hydrogens. Now, the reason I don't really emphasize it that much at this level is, one, it's my opinion, when you're getting simple splitting patterns, it's really obvious when you have a doublet or a triplet. Your doublet is going to be 2 side-by-side peaks, and they're going to be counted as 1. Your triplet, it's going to be really obvious that you've got this high center peak and 2 smaller peaks. I don't know how on earth you would end up getting a quartet. Well, you can. But as far as visually distinguishing between more complicated splitting powers, so let's say you had a doublet of a triplet, it would be pretty, in my opinion, pretty obvious when you get something like a doublet of a triplet. So that 1-to-2-to-1 ratio, it's true, and it's true for a lot of these peaks, that if you have a quartet, there's a setting of what those ratios would be. That said, I tend to include those in my tables, and most book tends to include those in those tables because, especially when you get a hydrogen atom, so let's say we have a hydrogen atom on a carbon that has 3 different types of hydrogens around it, you start getting really complicated splitting patterns, and even the NMR simulation software will sit back and say it's a multiplet. So those aren't the easier hydrogens to work with. So I will try to explain if it's like a doublet of triplets or something like that. But honestly, looking at the spectrum, this whole integrated area has to equal up to the area of that proton. And what ends up happening is when you start getting beyond triplets, so you start doing like a doublet of triplets, or you start doing quartets or things like that, your signal stops looking like this really well-defined peak. And you can kind of see this in the spectrum where I say it's a multiplet. It's a quartet of triplets. Is that it's right down here. And it gets really hard to see what's going. Now, this is a simulated spectrum, which makes it very clear, but if you're working with real-world data, there's going to be noise included with this as well, and you may not be able to see these side peaks off to the side. So, going back to the discussion board, how do we identify each of these? Well, you want to start with the simplest ones first, and then leave yourself with the more complicated ones last. So, I have to turn off this light for you to be able to see it. Turn off the other one. Sorry for how dark this is about to get. So we've got this carbon, and we've got 3 A carbons. So we'll do the carbon 13 first. We have 3 A carbons, 1 B carbon, 1 C carbon, 1 D carbon, 1 E carbon. So if we switch to our table, and that would make a lot of sense if I switched it to the desktop. We switch to our carbon 13 Nmr data. We only see 1 peak with an area of 3 in the carbon 13. So peak A here is going to correspond, peak 4 here is going to correspond to our A carbons. Now, as far as the rest of them, we're going to sort them by how much electron density they have around them. And so as the first pass, any carbon with a lot of hydrogen around it is going to be more shielded than one with less. So this shift at 15.1 ppm, this is the most shielded. This is going to correspond to your alpha group down here. So this is shift 5. And the rest, as we move down the chain, this carbon has 2 hydrogens, this has 2 hydrogens, this has none. This is going to be the most de-shielded. So this is going to end up being 1. As far as C and D go, we just expect this one to have a more shielded, it would be more shielded because the carbon beside it is more shielded. So it's kind of like that shielding, you're shielded because your neighbor's shielded. So in terms of order, this would give us 3 and 2. And again, this is for the 13C NMR. How about the 1H NMR? Well, again, make your life easier. These A atoms are all isolated. There's no adjacent hydrogens. So if we go to the tables of the 1H NMR data, there's only one that has an area of 9, and that's peak 3. Now we've got this 3-2-2 ratio. Well, there's only one carbon atom that has 3 hydrogens on it. That's carbon E, so that automatically defines E is the second carbon, and since carbon B doesn't have any hydrogens on it, it doesn't have a signal. So this leads us to question then, okay, what corresponds to peak 1 and peak 4? Is it atom C or is it atom D? And if we go back to that structure, atom C doesn't have any of the neighboring hydrogens in the D, so we expect C to be a triplet and we expect D to be a multiplet due to the hydrogens on C and the hydrogens on E. So D is going to be our multiplet, and if we look at the peaks, that's what we have as number 1. So number 1 is going to be our multiplet, and then we're sure carbon C is number 4 because it's the one with the triplet. So this is a solution to this problem. Atoms A correspond to peak 4 in the carbon 13 and peak 3 in the 1H NMR. B corresponds to peak 1 in the carbon 13, but it doesn't have an associated 1H NMR because it doesn't have hydrogens in it. Atom C corresponds to 2 in the carbon 13 and 4 in the 1H. D corresponds to 3 and 1, and then E corresponds to 5 and 2. And this is more or less how NMR is actually done in practice. We're just looking for self-consistency here. Does our molecule make sense with the peak we have? Now, for this, it's kind of easy because we built the molecule. I built the molecule and ran the simulation. But in practice, if you want to know which NMR corresponds to what molecule, you'll go through this process of elimination. Start with the easiest things first. If you have isolated hydrogens, figure out where their chemical shifts will be. Now, someone did actually notice, because I was reading their answers, that basically all these are predicted to have the same chemical shift. And so once we get to test 3, we start working with alkyl halides and alcohols, you can start getting more unique chemical shifts. So the chemical shifts get more diagnostic of what you have. So we're no longer just relying on the splitting pattern. But at this level, identify the simple ones first. And if you know something is going to be a big, nasty splitting pattern, if you see one particular peak that's a nasty splitting pattern, you can use that to kind of figure out which one it's associated with. And that's all the questions I received today prior to showing up. So it looks like nobody's really watching this, right? Oh, well, finally got some viewers. So what questions do you all have for me out there? No questions? I highly doubt that. Second question on the optical activity in the test study packet. Let me bring up the question packet. And this is for organic 1, for those of you who are listening but not seeing it. Still opening. So just got to ask the class grade on a curve. No, Weight Tech is not allowed to grade students on curves. So yeah, grade you get's the grade you get. We can't grade on a curve. Like, that's actually a policy for us. There are fantastic reasons for not grading on a curve. To be honest with you, the reason why universities grade on curves is it actually kind of it helps them control how many students pass on to the next level. So particularly beyond freshman year, they get a really good feel for how many students. They can actually manage it so they only produce so many graduates in a given field. And this is not me making this up. I did part of my graduate university work at University of California, Santa Barbara. And they determined that they were putting out too many graduates in a given year, so they actually reduced the curve for a course to fail out students, so their graduating class would only be a certain size. So if you're curious why four-year universities curve, that's actually the main reason. Is it helps a lot with the calculus in terms of how many students are going to have graduated in a given degree program and how many sophomores, juniors, and seniors they expect to have. It's really kind of weird. My goodness, this is taking its time opening. But yeah, I had a good friend who was at University of California, Santa Barbara, when they made that decision. And it was really kind of weird to realize a whole bunch of people were just getting arbitrarily failed out of the class. Okay, optical activity. Okay, so the way these are arranged are actually, I guess I can share my desktop with you. They're more vertical, and unfortunately it was just kind of the nature of the beast when I made this. So each column, you've got an associated reference activity, the actual optical rotation, the mass of the substance, the volume, the path length, and the enantiomeric purity. So you've got your formula. Alpha equals alpha D. If you're working with a dexter rotatory, if you're working with a levo rotatory, you'll get that number 2, times path length times the concentration times EE over 100. And I'm going to be honest with you, I need to look that up just to make sure that formula is correct. I haven't worked with this formula a lot. But I want to verify that formula is correct before I start walking down this pathway. Alpha times C times EE over 100. Yes, okay, so this formula is correct. So concentration, gram per milliliters. So you're given that information. Wow, these computers have a lot of issues today. So in the problem, we're given that alpha D. And you asked for, I think, the second question. Second question. So we're asked to find alpha D. We don't know this number, but we know that alpha here is 1.87 degrees. We want alpha D, the path length here. Our mass of substance, our concentration is 1 gram per 1 milliliter. Our path length is 1 centimeter. So 1 times 1. And the EE is 100%. So when we work it all out, the alpha D here is going to be 1.87. So it looks like it's actually a very easy problem. Let me download the answer key just to be sure. But yeah, it's really just taking that equation for optical activity and solving for the reference optical activity. So it's just a different variable within that equation. Second question on page 13. Oh, electrostatic potential maps. Oh, these are super easy. So electrostatic potential maps just show where the electron density is. So the more red it is, the more electron density you have. The more blue it is, the less electron density you have. And the more green is kind of a moderate level of density. Make sure I'm on the correct page. Oh no, that's page 13. Sorry, okay. You receive a sample of camphor from a manufacturer claiming to be enantiomeric pure. You dissolve 1 gram of camphor in 10 milliliters of water and measures this optical rotation of polarimeter with a path length of 2 decimeters. And that should be centimeters, not decimeters. For the results, you find the optical activity to be 7.8 degrees. Is substance optically pure or not? Optically pure. If not, what is the EE? So you still got the formula alpha equals alpha D times L times C times EE over 100. Now, on the course website, you can look this information up, or it's also available on the course website, but those tables, that alpha D is actually a physical constant that you can look up. So if you go to the course website under, well, actually, let me make sure I'm telling you this right. So Camphor, oh, I'm sorry. If you go up here, Camphor's optical activity is, wow, that made so much more sense. You can't see that though. So if you go to the table above it, we have Camphor's alpha D is 44.26. We're given that the concentration in this problem, we have 1 gram in 10 milliliters, so the concentration is 0.10. PathLink says decimeter, it should say centimeters. That's just an artifact of an old copy. And the question is our EE correct? Is it actually 100%? Well, if the optical rotation is 7.08 degrees, 44.26 times 2 times 0.01, if it's 100%, we should be getting 44.26 degrees. So this is not an enantiomerically pure material. It would have to give you basically something like 4.42 to be enantiomerically pure. So the 7.08 is implying that it's not enantiomerically pure at all. And then to solve for the E, you would just basically put the EE in as an unknown variable and solve for that. Although, yeah, actually it probably was supposed to be 10 decimeters to force you to convert. So 1 decimeter is 10 centimeters, so it's 20, 20. So 44.26 times 20 times 0.1 times E over 100 equals 7.08. And if I rearrange this, so I get 7.08 times 100 divided by 44.26 times 20 times 0.1. Sorry, 2 centimeters. It is supposed to be 2 centimeters. You get that the E here is 80%. Sorry, second guess myself on that. It should be 2 centimeters in that problem, not 2 decimeters. It's an old version of this problem. But yeah, you would, 2 ways you could test this. One, if it is pure, it's just going to be the concentration times the path length times the alpha D, which is in that table. If you don't get that number, it's not enantiomerically pure. If you're trying to figure out what the purity is, just leave the EE in as a dummy number. Again, this EE is in percentage because that's typically what we're reporting anyway. And when I work it out, I get 80%. No, those are good questions, actually. No, you're welcome. Again, optical activity, the theory is complicated. The application is just plugging numbers into an equation and solving. Some of the little errors you're seeing, the original formula that Carey and Francis Carey still puts in their book uses decimeters for some reason. And you have to go to the footnote to find the one that works in centimeters. I don't know about y'all, but I don't really work in decimeters, nor have I ever done so. And the centimeter formula is actually a lot easier to work with. It doesn't have weird conversion factors in it. Now that said, old equipment was sold in decimeter scales. So we actually had an old polarimeter that was in the lab. It was broken, but it had a 1 decimeter sample tube in it. But today we have like variable length polarimeters. We're trying to get them for Wake Tech. They operate in centimeters for this very reason. Nobody operates in decimeters. Right. Other questions? Can you give an example of 1H and 13 centimeter from the test packet? Followed by, for the lab report, since we didn't find the melting points in the lab, is it calculated for percent recovery the only thing you need? Yes, so for the results section, the percent recovery is the only thing you need to report. 1H and 13C from the Nmr test, from the test packet. Assuming I can get it to load. Why are you trying to open it from there? So let's consider the first problem on page, looks like 49. So the question is, which compound is consistent with the 1H NMR shown here? And you're given table below with peak A having chemical shift 5.26, peak B having a doublet at 1.54 in relative areas of 1 and 3. So the question is, which of these compounds is consistent? And I'm going to write them up on the board behind me here. The thing here is the ratios. So we see a doublet of quartets. That implies that there's 1 hydrogen near this one, and then there's also 3 hydrogens on an adjacent carbon. And this one sees a doublet, which implies that there's only 1 adjacent hydrogen. So if we look at these compounds, the hydrogens appear in a 3:1 ratio. So we have to have 2 unique sets of hydrogen, so 2 functional groups that are unique to being those types of functional groups, with their hydrogens appearing in a 3:1 ratio. So for this 4-carbon compound, there's 2 hydrogens here, 3 here, and for each of these alkenes, there's 1 hydrogen here and there's 3 hydrogens here. So we get the 1:3 ratio with these 2 compounds, but we don't get it for this one. Now the thing is that when we have them on the same side versus opposite, there's no difference here in the NMR. So we can't use the NMR to determine whether it's the one where they're together or one where they're opposite. So we would say that compounds A and C, these 2 compounds, which I think it actually gives the name of in the document, yeah, trans-2-butene and cis-2-butene, that's the only thing we can say is that they're consistent with the NMR, but we can't uniquely define one over the other. So if we go to the problem beneath that for the 1H NMR, which of the following compounds is consistent? We've got 4 unique positions, A, B, C, and D. Relative areas of 1, 1, 4, and 2. We have a singlet, doublet, and a pentet. So a pentet means that it sees 4 of the same carbons. So first of all, we need to see where we have hydrogens in compounds. This has 1, 2, 3, 4, 5, 6 different types of carbons. So that's not a possibility. This has 1, 2, 3, 4, 5 different types of hydrogen. I feel like I'm missing a peak somewhere. 1, 2, 4, 5. Pentet. Oh. Sorry, thinking this through. Yes, NMR is hard. Areas of 1, 1, 4, 2. 1, 1, 4, and 2. So your 1,3-cyclohexadione is going to be the one that works out. So your pentet, let's go to another problem. It's another one that probably would work better if I looked at it up at advance. Okay, so let's go to the one beneath it. Sorry. One beneath it, we have a single peak A, and we want to know which of these is most consistent with it. Well, we have a couple of possibilities here and you see this with one of the homework problems. The cyclohexane is consistent because all of these are the exact same hydrogen, so we should only see one peak, and since we only see one peak, your cyclohexane, you only see CH2 groups, you don't see anything else. The cyclohexane would work, but also your 2,3-dimethylpropane would work as well because all these hydrogens they're not next to an adjacent hydrogen. Now, as far as carbon-13 NMR goes, question is, we have a chemical shift at 27. It's a singlet. We have relative areas of 1. So if we look at the 3 compounds A, B, and C, we have cyclohexane, benzene, and 1,3,5-trimethylcyclohexane. Well, the 1,3,5-trimethylcyclohexane is not going to have one peak in it because we've got a methyl group, we've got a methylene group, we've got a methylene group. So that's out of the option. This leaves us with A and B. And the issue with B is that if you look up a table of NMR chemical shifts, which you have access to, you'll see that actually benzene rings are shifted down here below 60. So the only compound that this is consistent with here is cyclohexane. If we go down to the next problem, so we've got 2 chemical shifts, each are a singlet with relative areas. So this isn't the number of carbons, it's just saying, oh, hold on, someone's being a brat. Get down. Sorry. So if we look at this compound, we should have basically 2 unique carbons, each in a 1-to-1 ratio. So if we look at the 1,2-butadiene, we have a CH2 group, a carbon that's double bound to 2 carbons beside it, a carbon with 1 hydrogen hanging off it, and a carbon with 3 hydrogens around it. That's 4 unique carbons, so that doesn't work. We have 2 CH2 groups in this one, so those are the same. And then we have this carbon that's got 1 hydrogen sticking off of it, double bound to another, and a single bond to the other. This mirror image puts them in a 1-to-1 ratio. So B is consistent. With C, again, we see 1, 2, 3, 4 types of carbon. So those are the kind of examples of problems you would see with this 1H and carbon-13 NMR at this point. Mostly, can you see if it's self-consistent or not with the molecule that's drawn? So does that help with your questions about H1 HMR and carbon 13 NMR? You're welcome. Other questions? All right, so what's your question? Okay. Yeah, it's my computer's lagging a little today too. Um, Found out OneDrive was running everything. So now that I've shut down OneDrive, hopefully it will work correctly now. All right, so I'll give you all a few more minutes. If not, we'll take off about 5 minutes early. A reminder: next week you're going to see that the first test opens up. You don't have to take it Monday. You have until the following Sunday. It's available so that people will have access to the test if they need to take it early, meaning that Saturday and Sunday will be a conflict. Your homework is not due until the following Friday. So you have through all of next week until Friday to complete the homework, and then you're going to have the weekend to take the test. Now, I will try to check my email on the weekend, but again, it is the weekend. So again, I will try to answer it, but I probably won't be able to answer the test if you're in the process of taking it. But again, if you see anything weird on the test, so you take it and there's a question that's completely out of left field, let me know. Let me see what question you got, and I will take a look and see if that was a fair question or not. If it's not a fair question, I will give everyone back a point on that. I will give everyone back the points on the question. 20 multiple choice questions, worth 5 points each. No partial credit, which is the unfortunate thing. 75-minute limit, with the idea being that it kind of keeps you from Googling the answers. Now, it's going to be a mix of easy and hard problems, so it's not like you're going to be given 20 like NMR problems. You'll have questions like, what's the definition of an isomer? There's simple questions in there as well, moderate questions, and a sprinkling of hard problems. I don't think it lets you view all the questions at once, but that you can definitely go back and forth. So if you're getting stuck on a problem, you can definitely move to the next one and to the next one. Big reason I don't want to display all the questions at once is I just don't want you being overwhelmed looking at all the questions. So it lets you focus on one at a time. We do not have a live stream Monday. That's a holiday. I don't plan on being online, but you will definitely have the lab time to ask me questions next week. You'll have the Wednesday, Thursday, and Friday live streams. I am going to, particularly as we start getting closer to the exam deadline, I'm going to start being a little bit more judicious about the types of questions you ask me. So if you say, hey, I have an oddly specific question to ask you, I'm probably going to make sure that's not a test question that you're currently working on. So again, try not to lead me to that suspicion. But again, you definitely have next week to ask me questions, and then you have the weekend to take the exam. All right, if there are no more questions at this time, I'm going to go ahead and sign off. Again, email me questions if you can't make it to the live streams. More than willing to answer them for you at the start of the live streams. And I will see you all next week, but not Monday.